In the first part, we have seen the various structural components, how it is affected by the corrosion. And now in this is the second part, how the corrosion takes place within this structure. That is the second part. Now you see this figure, how concrete cross section is there. It is a highly magnified structure. The circular things are the pores, and pores are connected by the capillary pipes. Capillaries are very small, tiny pipeline like, and all pores are connected. And this is the surface. The vertical line is the surface. One pore is shown here, and pore is being when you are curing it or when the moisture, this water gets penetrated through the capillary and reaches the voids and reaches a void, next void, like that. It all and capillary pores also filled with the water, and this water will be converted to calcium hydroxide, because calcium oxide is more, about 62 to 65% is there in the cement, and that calcium oxide mixes calcium silicate it forms, and then remaining residual calcium combines with the water and it becomes the calcium hydroxide. This pore water mainly consists of calcium hydroxide. The chlorides in the environment gets into the pores again. From the environment it gets into that. It travels through the capillary pores and reaches. The two main culprits for the corrosion of steel in concrete is, first one is the chloride. This is a major culprit, chloride. Second one is carbon dioxide. These two are main problem creators. The chlorides, it's just from the environment up to 2 kilometers long from the sea coastal line, is chloride laden area is more. So the chlorides just goes into the concrete through the pores, voids, cracks, fissures, and many more surface defects. It's all get into it, and then it travels and it goes through permeation, chemical bonding, everything is taking place. Now, when it is being absorbed, the chloride get into there are three kinds of chloride, I can say. One is free chloride, next is adsorbed chloride, third one is the combining chloride. Free chloride will not absorb in the pore walls. Chloride will travel through the pores, capillaries, everything straight away. Second one is adsorbed chloride, will get absorbed into the pore walls and it will not travel. And third one is absorbing chloride. The chloride will be absorbed by the concrete. It will be converted into chlorosulfoaluminates. Sulfoaluminates are there, that chloroaluminates, it forms chloroaluminates, and it will remain there in the thing. It should not be, it is not allowed, but it is not harming, it goes inside and which is that. The free chloride only will travel through that, pores, voids, and pore connectivity is very, very important for this structure. If pore connectivity is not there, it will end. It will travel, it will try to pull. It will be somehow, it will be traveling through the concrete and it reaches the steel. Steel is positively, that is Fe plus, and chloride is a chloride minus, Cl minus. So this steel attracts the chlorides and comes there, but it will not immediately get corroded, because steel surface, there is a coating called, that is passive film, which the thickness is 0.002 mm thickness. So that is called passive layer, that is protecting the steel. These chlorides which are penetrated, it will be deposited on the surface of the rod, that is over the passive film. When the threshold limit of the chloride is reaching, then it will damage the passive film and it will touches the steel rod. Once this steel rod chloride touches the steel rod, bare steel, then corrosion process starts. That point will act as an anode. The rest of the area will act as a cathode. When the ratio of cathode to anode is large, the corrosion is very fast. That is the thing, it is taking place in this year. Cathode area is more, anode area is very small. That is the corrosion will be fast. The electrons will go from anode to cathode, from cathode to anode. this is a one cell is formed. This is left unnoticed means then corrosion will be continuing one place. And other place also there are so many anodic zones can form. So this has to be viewed very seriously. This is how the corrosion damage starts. So this is how I told you now that the corrosion once it reaches the brown color over the rod, see the anode spots, it is being eaten away very fast. Chloride becomes very chloride, see, and releases like this. These are the equations taking place at the anode and cathode zone. And this is somehow it is, see, hydrophobic pore blocking. You can prevent it by giving some anodic pore blocking coatings, some silane, silaxine, like that, some core painting can be done, and then the water entry can be prevented. You see here the rebar is nothing but the reinforcement, and over which the yellow lines as the passive film. It is not being affected by the chloride because water entry or chloride entry is restricted at the surface itself. Chloride induced deterioration process for structural element. Here it is a schematic, that's a graphical illustration. Initially it is initial cracking. So once the surface defect or initial cracking is there, then through which the diffusion takes place, the corrosion takes place next step. And once the corrosion is initiated, it is a very rapid deterioration starts. That is the very steep line. And there is a function that deterioration, if you can allow like that, there is a certain limit up to which we can allow corrosion. After that, beyond that, it will go. Then afterwards, failure comes. In the marine structure, it is a submerged structure. High tide and low tide is there. That is, this tidal waves, it's getting the abrasion. It gives abrasive forces, and concrete is getting abraded, and it is also chemical attack also is taking place. Rats will be exposed in certain time. The influence of chloride goes up to 2000 meters from the coastal water line. You see, it is around up to 2 kilometers. One should be very, very careful. Chloride component, how much ppm will be there, it is being shown at the bottom. Zero line, 100% if you take it at 2000 meters, it 4 ppm. See here, this is another type of corrosion. It is being included here. It is called stray current deteriorate. Stray current is nothing but the leakage of current. Leakage of current can be encountered when railway line is there, electric railway line is there. Somehow the earth is being given to the rail at the bottom. That will be circulated and it will be relieved that thing at one place in the ground. That will become the anode spot, and that you see the corrosion will take place at that point. When cathodic protection is given to the pipelines, and that pipeline corrosion current also travels through that. So the corrosion may take place nearby structures. And this is a drain, circular cross section. You can see the drainage water when it is going. Microbial activity will be more in that wastewater. So what happens, that releases vapor, hydrogen sulfide, that it goes, mixes with the oxygen present above the water and goes up to there, up to the wall, getting condensed. And then it comes into H2SO4, sulfuric acid comes. That sulfuric acid, highly corrosive and gets deteriorated. You can see the drainage pipe inside circular at the top can be deteriorated because of the H2SO4. It's also again same. H2S is converted into H2SO4 in presence of oxygen and then gets descent. This is a circular thickness is getting varied. That is what it is illustrated in this. See here, this is a protective layer in the passive film. That is the green line. That is the passive film, is the protective layer. I told you up to 6.5 times the rust is getting converted. These are the oxide component at various level. If you take Fe is a 1, and due to corrosion, the chloride attack, it can go up to 6.5 times this behavior. Just to imagine how 6.5 is such a voluminous expansion that is taking place due to corrosion. That is why the delamination of the concrete and other things takes. These are the various oxide components stage by stage to reach that is 6.5. Again, that is given in name different names. That oxide names different names. That's all. See, I told you the moisture and the soluble salt from the marine environment goes there. It reaches the steel. It gets accumulated, and then oxygen also it helps. It's a full rod. Then it is getting cracked due to rust product, and this is again the rust product is accumulating, and then it gives a crack. And third one is a spalling is taking place. And this is also the same thing, same thing only. Wherever the pores and voids are there, the rust product also travels through that also. This is corroded steel shown in two sides. One is the bare steel. Initially it was like this on the left hand side. Right hand side, the rust product is being built up, and the bonding of the rod with the concrete is highly important. Otherwise, a force transfer will not take place. And here you see, when the rust product are there in between the concrete and the steel surface, the rust product prevents the bonding, and this is one of the drawback. Also, cracks are there. Cracks are weaker parts, as you know very well. And these are the principal stresses and the crack formation. You see that the crack is formed, and this is a diagonal crack is formed because of the resultant forces acting on the right hand side shown the rebar. And this is the principal stress. The stress components are shown in here. This is a rust product accumulated. It travels, and then spalling or deterioration takes place, and the concrete comes down because of the pressure. This is the thing that it is being measured. Here you see the anode cathode area of the steel rod embedded in concrete. Corrosion cell is formed, and corrosion current is being measured. See, this is offset potential. Reference electrode is connected to the steel reed bar, and then the other end is connected to the voltmeter, and then voltage is measured, and from that measured voltage it is being determined, identified the area which is affected, which area is anode, which area is cathode, can be measured by this surface area measuring potential measuring. And this is the thing. Rebar is corroded and get cracks A and B, where the steel stress is more there in the second figure. Third is the because concrete is cracked, there is no A and B, there is no stress. And these are the bottom three diagrams are how the bond force between the A and B. A lot of work is going on in this area. This is how this entire thing can be the service life model. Loss of protection means corrosion initiation, cracking, delamination or spalling, and extensive spalling are taking place at that point, and then it's a catastrophic failure, collapse taking place. The potential, how the potential is measured with the millivolt, this voltage voltmeter. Again, this is also open circuit potential measurement, and here also they use this sponge and this electrode, calomel electrode is used. See, so far what we have seen is chloride, how the chloride affects the structural components. And second thing is the carbon dioxide is another culprit. What happened? The pores within the pores of the concrete, calcium hydroxide is more. When carbon dioxide comes and goes inside the concrete, the carbon dioxide mixes with the pore water, which is consist of calcium hydroxide. This calcium hydroxide mixes with the carbon dioxide, and calcium carbonate is precipitated within the pores, and carbonic acid is formed. Carbonic acid and calcium carbonate are formed within the pores. This acid component mixes with the steel, the pH of the concrete goes down. As long as the rod within the concrete, you know very well that it is highly alkaline material. This alkalinity is reduced by the carbonic acid because of carbon dioxide. This is called the carbonation of concrete, which reduces the pH of the concrete and corrosion takes place. This kind of deterioration you can see from the corner of the column getting deteriorated, and a vertical line of crack at the corner of the columns can be seen, very much have seen. So that is because of carbonation of concrete. See here, this is the concrete exposed to carbon dioxide, nothing is there. When carbonated concrete is plain, uncarbonated is seen in the pink color. The carbonated will be no color change. This is how you can take a piece and then spray it with the 1% naphthalene spray, and we can come to this. Pink area is not carbonated, surrounding is carbonated, means plain area. Repairing is important for the corrosion. You see this carbon, this is a deterioration starts, and the life of the concrete is gradually coming down on the left hand side triangle, and at one end, if you have not attended the repair, the life will be only up to there, service life. And next, if you attend a repair, and then its service is increasing, and then service life of the structure is getting increased. This is a schematic review to represent how to increase the service life of a structure. To conclude this, we can say the chloride and carbon dioxide, how it gets into the concrete, how the deterioration takes place, and how important the repair work. All these things we have come to know in this part of thing. And next part, we can see how to mitigate this corrosion.